This is section 3.3 in Precalculus. And today we're going to review everything you learned back in Algebra 2 related to rational functions. And when I say rational functions, we're talking about fractional. Okay, the parent function that we learned in the last unit, 1 over x, is a rational function. So it's the ones that have the asymptotes, and could be both vertical and horizontal, or one or the other. Okay, so take a look. First, we want to kind of talk about this concept of continuity. So when I look at this graph, and I said it before, you read a graph just like you read a book. You start on the left, so I'm going to start right over here, and you hop on the graph, and you just start moving towards the right on the graph. Okay, so as I move along towards the graph, I see that there's a hole. Now, the way we write it down on paper is to show this kind of open circle, but the way it actually is, like if you were to actually look at the graph of this, you don't kind of see an open circle, you just see a space in the graph. Okay, so there's a hole, there's a break in the graph. That's what that means. I'm going to put the hole back because, again, that's just kind of how we show it here. So in this case, because there's a space in the graph right there at x equals -2, we would say this function is not continuous at -2. All right, as I keep on going, moving towards the right, the graph shoots down to the bottom, and in order to get from this spot on the graph over to this spot on the graph, there's another break in the graph. There's a vertical asymptote. So that means this graph is not continuous at x equals 1. And then if I keep going, if I keep moving to the right and I get to this point, and then there's a giant space in the graph before I hop on down here and start moving over. So there's another break in the graph at at x equals 3. So we would say there are 3 places on this graph that are not continuous at those 3 x values. Okay, so not continuous, not connected, however you want to think of it. So discontinuities occur when the function is undefined. Okay, so in other words, when the equation is undefined. So remember, a function's undefined when the denominator equals 0. When the denominator equals 0. And there's 2 types of discontinuities on these rational functions. There are holes and there are vertical asymptotes. So if you look up here at this graph, there was a hole right here at -2. There was a vertical asymptote right here at 1. And there was a giant break in the graph over here, but there was definitely a hole. So holes or asymptotes. All right, so let's first of all refresh your memory on holes. So holes occur when you have factors that cancel. Now, in order to know if you have factors that cancel, you need to factor your equation. You need to put it in factored form. So I'm going to try and factor both the numerator and the denominator separately. Well, in the numerator, I can write that as x plus 3, x minus 1. Denominator, I can't do anything, so I'll just leave it as x minus 1. And I'm sure you can tell at this point, these are the factors that cancel. So all I have left is the x plus 3. Okay, so since I had factors that cancel, that means there's a hole on this graph when x equals when x equals 1, because it's whatever makes that factor equal 0. Now, a hole is one specific point, right? If you look up here, the hole was one specific point on the graph. So yeah, I know where it occurs, x equals 1, but I also would like to know what the y value is. Like right here is where x equals 1, but is the hole right here when y is 2? Is the hole up here at 5? Is the hole down here? All of those places are when x equals 1. So I need to get more specific and write it as an ordered pair. And we've said this before, anytime you have an x and you're trying to find the y, you just substitute that into the equation. So if I put a 1 in for x, I'm going to have f of x equals 1 plus 3. So the whole is at 1, 4. So right there is the whole. What is the rest of the graph? Well, go to your simplified version of the equation. What is that the graph of? Isn't that just a line? Think mx plus b. So y-intercept of 3 with a slope of 1, up 1, over 1, as far as you want to mark it off. So if I were to draw this line, it's something like that, but keep in mind we had a hole right there. So in this case, it was a line that had a hole in it. Okay. So the other kind of discontinuity are vertical asymptotes. All right, so when do you have vertical asymptotes? When the denominator equals 0. So remember, we're going to factor it, and if anything cancels, yeah, that's going to be a hole. But if there's anything left in the denominator that could make the denominator equal 0, that's when you have a vertical asymptote. So let's take this function, factor the numerator and the denominator. So the numerator I can't do anything with. Denominator, I'm going to write that as x plus 4x minus 1. I think that's going to work. And so in this case, yeah, I do have a factor that cancels. So there is going to be a hole. Let's simplify. Sorry about that. So what I have left over here is 1 over x minus 1. Okay, so like we started to say, yes, there's a hole. The factor that canceled was x plus 4. So the hole is at negative 4. Remember, it's whatever makes that be 0. How do I know what the y value is? Well, plug that negative 4 in for x into your simplified version of the equation. And if I do that, I'm going to have y is 1 over negative 5. So that means the whole is at negative 4, negative 1/5. So right down here is my whole. How do I know what the rest of the equation looks like? Well, look at the simplified version of what we have. So in this case, how do I know for sure we're the vertical asymptote? Well, what's going to make that denominator equal 0? Here's the denominator. Won't that be 0 when x equals 1? So that's how I know there's a vertical asymptote at x equals 1. Make sure you draw that in. Notice the difference in how I present my whole and my vertical asymptote. The whole is an ordered pair, but the vertical asymptote is a vertical line. So you have to write it as the equation of a vertical line. So x equals whatever number. All right, so back to what I was saying. How do I know what this graph looks like? Well, look at the simplified version of the equation. Isn't this just the parent function 1 over x that's been moved 1 unit to the right? And so if it's the parent function 1 over x, yeah, I've got my vertical asymptote, but don't I also have a horizontal? And I know that I could graph this. Remember, it goes through this point, and it goes through this point. Just make sure when you draw it, that as it gets closer and closer to that asymptote, that it goes through that hole. So again, don't forget we had a hole right there. So this just happened to be the 1 over x graph that has a hole in it. All right, so what do we have? It says without graphing. So this time we're not going to go as far as to graph, but let's just think about find all holes and vertical asymptotes. So remember, the key here is factor everything. So let's start by factoring. I'm going to say x plus 3, x minus 1. Excuse me. So in this case, I know there's a hole when x is 1. And remember, if I write down my simplified answer, I just have x plus 3. And so if I want to find the y coordinate, I'm going to plug that 1 into my simplified version. So my hole's at 1, 4. In this case, there was no denominator left, right? It canceled. So that means there is no vertical asymptote. Okay, sometimes you don't have one. Look at letter B. So if we factor this one, the denominator is going to become x plus 4, x minus 3. Let's see, just making sure that works. Yeah, that way I have a positive 1x in the middle. Nothing cancels. Okay, that's fine. That means there's no wholes. No factors canceled. But in this case, I have 2 factors in the denominator. That means there are 2 vertical asymptotes. So vertical asymptote when x equals -4, but also when x equals 3. It is possible to have 2 vertical asymptotes. Okay? All right, so look at the last one. Again, we want it in factored form. In this case, I can factor both the numerator and the denominator. So let's see, a -3 and a +1. That'll give me the -2 in the middle. And down here, I think I want -3 and +2. And that'll give me the -1 in the middle. All right, so in this case, I have the x minus 3's that cancel. So there is a hole when x equals 3. And so remember, in order to find the y-coordinate, you look at the simplified version of the equation. If I plug a 3 in for x, everywhere I see an x, I'm going to get 4/5. Okay? And in this case, there is still a factor in the denominator, so that means there's going to be a vertical asymptote at x equals -2. So I want you to look back at what we did here. I had one scenario where there was a hole but no vertical asymptote. I had one scenario where there was no holes, but there were multiple vertical asymptotes. And then I had another scenario where I had both. So it could be any combination of holes and vertical asymptotes. So let's talk about horizontal asymptotes. Again, it seems like we're doing a lot in one section here, but you did all of this back in Algebra 2. Okay, so horizontal asymptotes. You might not have heard them described this way, so it might sound a little different. We're still going to, refer back to the same way you learned how to do it, but I want you to think about this. Horizontal asymptotes describe the end behavior of a graph. Okay, horizontal asymptotes describe the end behavior, meaning what happens on the ends, the far right and the far left. Horizontal asymptotes are not about what happens in the middle. In fact, you may have been told by some teachers that asymptotes are the lines that your graph never crosses. Well, that's not true. It's not true. It's true about vertical asymptotes. Your graph will never cross a vertical, but your graph very well could cross a horizontal. But if it does, it's going to be in the middle of the graph, not at the ends. So, in other words, a horizontal asymptote shows where the y values level off. Okay, it shows where the graph levels off, or the y values level off as the x values get increasingly large, meaning as you go out to the far right of the graph, or as the x values get increasingly small, meaning you're going out to the far left side of the graph. But again, you're going out to the ends of the graph. And the way we tend to write the notation, as x values go out to the far right, we tend to say x approaches positive infinity, or as you look out to the far left, we tend to say x approaches negative infinity. It's just kind of a notation to say go to the right or go to the left. Okay. Now here's the part that you probably do, hopefully you remember a little bit about. This is how you were taught to find horizontal asymptotes. So in order to find them, you are going to compare the degree, meaning the exponent, of the numerator and denominator. Okay, so case number 1, what if the numerator degree is less than the denominator degree? An example might be, let's see, y equals x plus 1 over x squared minus 10. So the degree of the top is 1, the degree of the bottom is 2. So the numerator is less than the denominator. In that case, we would say the horizontal asymptote is y equals 0. Okay? The second case is, what if the numerator is greater than the denominator? So the example might be just the opposite. Like, what if we have x squared minus 10 over x plus 1? So again, the degree of the top is 2, the degree of the bottom is 1. So the numerator degree is greater than the denominator degree. In that case, we would say there is no horizontal asymptote. And then the third case, what if the degree of the top and the bottom are equal? So maybe you have y equals x squared minus 10 over x squared plus 1. Again, that minus 10 and that plus 1 have nothing to do with the horizontal asymptotes. It's all about the degree of the top compared to the degree of the bottom. So in this case, they were the same. And so on these, for the horizontal asymptote, we say y equals, and then you look at the coefficient from the numerator and the coefficient from the denominator. So I'm going to say numerator coefficient over denominator coefficient. So on this particular example, the coefficient on the top was a 1 in front of the x squared. On the bottom, it's a 1 in front of the x squared. So on this particular one, the horizontal asymptote would be 1 over 1, which is 1. Okay? So I'm going to reiterate what I said earlier. Keep in mind, a graph will never cross a vertical asymptote. Okay? But it can cross a horizontal asymptote. Okay, and if it does cross a horizontal, it's usually going to be in the middle. Just to kind of show you a little bit of an example. Maybe I have I'll put it in green, a horizontal asymptote here. It's possible that when you graph it, somewhere that maybe on this side it levels off at that number, but who knows what happens. See how I crossed it right there in the middle? But then, as I go out to the far right and the far left, it's still leveling off at that asymptote. Okay? So, let's look at these. So, we're not going to graph right now. Let's just practice using these rules. And by the way, I should mention, a lot of teachers teach this thing as the Bobo-Botten. Does that sounds familiar? I'm going to write that here. But that's only helpful if you know what it means. Bobo-Botten. And the part that everybody tends to forget is where they say eats DC. I know that's weird. And again, you can use that if you want. I don't usually go to that just because, I don't know, I'm not about cutesy stuff, but whatever. So the Bobo, that's where they're saying bigger on bottom. Well, if the numerator is less than the denominator, then the denominator is bigger on bottom. So bigger on bottom. And when it's bigger on bottom, the horizontal asymptote is 0. Or the next one, if it's bigger on top, right, the numerator had a higher exponent than the bottom, that's the case where for the answer there are no horizontal asymptotes. It's funny, people usually just call this Bobo-Botten. They forget the eats DC, mostly because they don't remember what the letters stand for. But they don't really need to remember what the letters stand for because they usually know the rule. Hey, if the degrees are equal, you look at the numbers in front. But what this means is equal and the same. Okay, so equal and the same, which is kind of redundant if you ask me. But so if the numerator and denominator are equal in degree, then in order to get the horizontal asymptote, you divide coefficients. Divide coefficients. Okay, so however you want to remember it, you need to know those rules. So let's practice. When I look at letter A, if there's no x up there, it's kind of like having an x to the 0. So here's a case where it's definitely bigger on bottom. So the answer is y equals 0. Okay, here's a case where the degree of the x's is the same. So that means I'm going to look at the coefficients, and the coefficient here is 1, the coefficient here is 3. So my horizontal asymptote is at 1/3. On this one, I have a degree of 1/2. So this is the one where it's bigger on bottom. So y equals 0. Notice on this one, the degrees are the same. Exponent on top is 2. Exponent on bottom is 2. So I look at the coefficients, 3/1. So the horizontal asymptote is 3. Okay, here's a degree of 1 over a degree of 3. So bigger on bottom, y equals 0. Now on this one, you have to picture if it were multiplied out. So if this were multiplied out, and you don't actually have to do the FOIL, but can you see that if this were multiplied out, wouldn't the first term be an x squared? And so if the first term is an x squared, you can tell it's going to be bigger on top. And so this is the case where there are no horizontal asymptotes. Okay. Now, we're gonna put all of this together in a minute, but one thing that's kind of helpful is just a reminder when we get ready to graph. It's just a reminder of, remember, the x-intercepts are called the zeros of the function. So basically, that's what makes the function equal 0. Or you might say, hey, the y-coordinate is 0, right, for your x-intercept. All of these things are true. Well, whenever you have a fraction, the easy way to find x-intercepts is to just look at the numerator and see what makes the numerator equal 0. So that's kind of an easy way to find x-intercepts on rational functions. And then don't forget, for y-intercepts, that is when the x-coordinate is 0. And then you're finding the y. Okay. So let's put it all together. We're going to find all the vertical asymptotes, the horizontal asymptotes, the holes, any x or y intercepts, and we're going to use all of that to sketch the graph. All right, so vertical asymptote, the denominator would be 0 when x equals -3. There are no holes because there are no factors that are going to cancel out. And I can tell there's a horizontal asymptote because the degrees are the same. I look at the coefficients. So there's a horizontal asymptote at 1/1. So let's put that on. X equals 3 is my -3. Almost got that in the wrong place. -3 is my vertical. Y equals 1. And when we're doing these, make sure you extend them kind of well out beyond the axes. We want to see a full graph. We don't want to see any little partial graphs just because it's all smushed to the side. And then in this case, now I can't just automatically put it in the, kind of the top and the bottom like a 1/x graph because this isn't 1/x. It's x over x. So it might look the same, but it might not. So we have to check a few things. So let's think about x-intercepts. So remember what I said earlier. X-intercepts are going to come from the numerator. Well, what will make x minus 5 equal 0 is if x is 5. And then remember, y-intercepts are when the x-coordinate is 0. So if I want to know what the y value is, plug 0 in for x. So on top, I'm going to have -5, and on bottom, I'm going to have 3. So let's put those on. I know I have an x-intercept at 5, 0. And I have a y-intercept at 0, -5/3. Isn't that like -1 2/3? Something like this? Okay. Well, I know when I have asymptotes, I know that my graph always approaches the asymptotes. So as I go out to the far right, it's got to approach this asymptote, but it's got to go through those points. And as I head this direction, it's got to finish approaching that asymptote. And here's the thing, you might say, okay, on this side. So on the right side of this asymptote, my graph is either up here or it's down here, but not both. I'm just telling you that's how asymptotes work. So how do I know if it's on top or on bottom? Well, because remember we said the only x-intercept we have is this one right here. So in other words, it's not going to cross the x-intercept, it's not going to cross the x-axis anywhere over here. Well, if it's not going to cross the x-axis, then that means it has to be, the graph has to be up here. Okay, so yeah, it kind of looks like a 1 over x graph that's been flipped over, but it's not exactly the same. Okay, so let's look at number 2. Let's fill in all the information we know. Before I do anything, I want to put it in factored form. So I'm going to say y equals x minus 2. How about x plus 4 and x minus 2? Right? So since those are canceling, I know there's going to be a hole at 2. But let's always get in the habit of writing your simplified version. So this is going to simplify to be 1 over x plus 4. And that's helpful. It's helpful to have that because that's going to help me know what my final graph looks like. Okay, but let's fill in all information. Vertical asymptote when x equals -4, because that's what makes the denominator equal 0. And so we said, I know there's a hole at 2. In order to find the y value, plug 2 into your equation for x. So we're going to have 1 over 6. Okay, what about horizontal asymptotes? Well, you can either look at the original equation to compare the degree, or you can look at the simplified equation to compare the degree. It does not matter. You're going to get the same answer. So let's say I look up here at the original. It's definitely bigger on bottom. So the horizontal is y equals 0. Okay, for x-intercepts, look at your simplified equation. Will the numerator ever equal 0? Well, the numerator is 1. That's never going to equal 0. That means there are no x-intercepts, which you might think, oh, what's the point? Well, because that's super helpful. I know this graph is not going to cross the x-axis, okay? And then for the y-intercept, so remember for the y-intercept, that means x is 0. If I plug 0 in for x into the simplified version of the equation, I'm going to get 1/4. Okay, so let's put everything on. I have a vertical at -4. I have a horizontal at 0. This graph has a hole at 2/1/6. So right here, there's a hole. There, it's never going to cross the x-axis, and there's a y-intercept at 0/1/4. Okay, so if I were to sketch this graph, I know it approaches this asymptote over here. It goes through the hole, heads for that point, and then it continues over to head, okay, that's terrible, to head up towards that asymptote. Okay, now how do I know on the left side of the vertical, how do I know if it's here or here? Well, in this case, look at the equation, look at the simplified version of the equation. Isn't it just a 1 over x graph? And I know what 1 over x graphs look like. They are in the top and then the lower left side. So over here. Okay. A couple more examples. I know there's a lot of examples, but there's a lot of possibilities to show. So let's look at the next one. Put it in factored form. So I'm going to say x plus 3, x plus 2. But we'll kind of pick up the pace on finding information. So we definitely have a hole at -3. Notice the only thing I have left for my equation, I always write down my simplified version, is x plus 2. Nothing left in the denominator, so that means there aren't any vertical asymptotes. Let's finish out the hole. If x is -3, plug that into your simplified version, then the y is -1. It's not a fraction anymore, so there are no horizontal asymptotes. X-intercept is whatever makes the numerator equal 0. Well, you can kind of picture this as like being over 1. So what would make x plus 2 equal 0 if x were -2? So the x-intercept is at -2. And remember, the y-intercept is when x is 0. If you put a 0 in for x into the simplified version, you're just going to get 2. So let's put this on. I have a hole at -3, -1. So there's a hole. I have an x-intercept at -2. I have a y-intercept at, something's wrong here. Let me see. How come something's... Oh, look, I'm being dumb. The whole was -1. Sorry about that. You probably already noticed it. The whole was -3, -1. Okay. The x-intercept was -2. The y-intercept is +2. It looks like these points are just lining up on a line. Should my graph look like a line? Well, yeah, look at your simplified version of the equation. It's just x plus 2. Isn't that like mx plus b? Isn't that just a line? So if I don't even have to mark off my y-intercept or my slope. I've already got these 3 points that are going to help me know where this line goes. So it's something like this. Again, make sure you notice that there was a hole right in there. So yeah, my equation was just a line. So it started out as a rational function because I had x's on top and bottom, but it simplified down to being just a linear equation. Okay, that might happen. Let's do one more example. Let's see if there's anything different with this one. So if I start doing my factoring, let's see. On top, 2x and x, I need 5 and 1. These are all going to be pluses. Okay, and the denominator, x plus 5, x minus 5. So I do have the x plus 5's cancel. That means there's a hole at -5. So let's write down our simplified equation. 2x plus 1 over x minus 5. Since there is a denominator, I know there's going to be a vertical asymptote at 5. For the horizontal, I'm going to compare the degree. I tend to go to the original just because it's not cluttered up. So for the degree, I can tell it's a square on both the top and the bottom. So I look at the coefficients. It's going to be 2 over 1. So y equals 2. X-intercept. So remember, for the x-intercept, you look at the numerator. So the numerator was 2x minus 1. What's going to make that equal 0 is if x is 1/2. And then for the y-intercept, I know that the x-coordinate is 0. So if I plug a 0 into the simplified version of the equation, here's my simplified version of the equation. If I plug in a 0 for x, I'm going to have 1 over -5. Okay, so let's put everything on. Vertical at x equals 5. Horizontal at 2. Y equals 2. Notice I'm extending these way out. X-intercept at 1/2. Y-intercept at -1/5. Oh, look, I forgot to finish out my hole. Sorry about that. So if the hole is at -5, I need to put a -5 in for x. So that's going to be -10 plus 1 over -10. So -9 over -10, so 9/10. So at -5, 9/10, right up. Let's see here. Hold on. Oh, look, did you see that? I was being dumb again. The x-intercept is going to be -1/2, right? Oh, this was a 2x plus 1. So the x-intercept is -1/2 right here. Sorry about that. And then our hole was at -5, 9/10. So right in here, I'm just kind of guesstimating 9/10 is going to be really, really close to 1. So I can tell, I know exactly what the graph is going to be in this part because I have a bunch of holes. I know it has to level off at the asymptote. I know it's going to go through all right. I know it's going to go through. I have to try and make that look a little more. There we go, something like that. And so on the other side, how do I know if it's up here or down here? Because it could be either one, right? It doesn't have to be opposite. Frequently it is, but it doesn't have to be. But what I do know is that there aren't any x-intercepts over here because there was only the one x-intercept. So if it's not going to cross the x-axis, that means it must be up here. Okay, so those were a lot of examples for rational functions.